to our machine design series, where today we are talking about bolt preload. We've just wrapped up our video on external loads and established how important it is to have an adequate preload in a bolted joint. And now we're going to discuss the very practical matter of how do you decide how much preload to apply to your bolted joint. So let's get into it. First, let's talk about the strength of a bolt and how to determine a clamp load based off of the material property of the bolt. So tensile strength is the material property that's most widely used to analyze and describe threaded fasteners. And there are two tensile strength properties that we often talk about. One is the proof strength, which is the tensile stress that can be applied without permanent deformation. And then there's the yield strength, which is the tensile stress at which a specified amount of permanent deformation will occur. All right, so here's our written out definitions for proof and yield strength. Proof strength is also, it's called the proof strength because this is the stress that manufacturers will apply to a few fasteners out of a specific lot and literally prove that those fasteners can withstand that level of stress without any permanent deformation. Whereas the yield strength is the same kind of yield strength that we think about with any material, and usually the specific amount of permanent deformation is that 0.2% offset yield strain. We typically want to design a bolted joint that functions in the elastic range, meaning that we want to operate below the proof strength typically, and definitely below the yield point. So we want our threaded fastener typically to be able to return to its original shape with no permanent deformation. So with that in mind, let's draw a typical stress strain diagram for a steel bolt. All right, here's a typical stress strain diagram for a steel bolt. Notice that we've labeled the proof strength and the yield point here. The proof strength is typically going to be about 90 to 95% of your yield strength. The clamp load or the preload that we want to apply to our fastener has got to be less than this proof strength. And there are a couple of guidelines depending on the type of bolted connection that you are designing. So our typical clamp load is going to be about here. And we will want to apply about 75% of the proof strength to our fastener if it's going to be reused. And we can go up to 90% of the proof strength for permanent fasteners. There are tables in your textbook. I'll write out the table numbers here. So tables 8-9, 8-10, 8-11 in your Shigley textbook contain material properties for different grades or classes of bolts, and bolts will have a marking on the head of the bolt that will indicate the grade or class of that bolt. So for example, a grade 8 bolt will have these 6 radial line markings on its head. I can try to draw that. So if you see a grade 8 bolt, it might look something like this, where it has these 6 radial line markings on its head to indicate that it is a grade 8 bolt. For a grade 5 bolt, you would have 3 markings. A grade 2 bolt or an ungraded bolt will have no markings. And then in the metric system, you'll have a class of bolt, and that will just be indicated by class number on the head of the bolt. So it's a little bit more straightforward. So I'll do just a quick example of that for a class 8.8 metric bolt. You would just simply have this 8.8 on the head of the bolt. So I encourage you to go take a look at those tables in Shigley because it gives you the full listing of all the different bolt head markings you might see and their corresponding grades and classes. And then remember that those grades and classes tell you the material properties of the bolt. So if I have a grade 8 bolt and the size is between, let's say the diameter is between 1/4 inch and, let's see, 1.5 inches. As long as the diameter of the bolt is within that range, then I know from this table that my proof strength, which I'll designate SP, is 120 KSI, and I also know that my minimum tensile strength is 150 KSI, and that my minimum yield strength is 130 KSI. So you can find all of this. This is from table 8-9, and with this proof strength, you can determine the clamp load that you want to apply, depending on whether your fastener is going into a permanent joint or one that might be disassembled in the future. I should note that nuts are also graded so that they can be mated with their corresponding grade of bolt. The purpose of the nut is to have its threads deflect to distribute the load of the bolt more evenly to the nut. So it does matter if the grade of the nut mates with the grade of the bolt that you're using. Now let's turn to the even more practical matter of how do we measure the preload to ensure that we've applied an adequate preload in our bolted joint. And we have quite a few different options, so let's discuss just a few of them. All right, so let's talk about a few different preload measuring methods. We're going to do so in this table that I've set up, and we'll compare the % accuracy of each method along with the relative cost. So first up, let's think about the simplest possible preload measuring method, which is just doing it by feel. No special tools, just use operator's judgment. I'm sure we've all done this, right? Whether it's complex machinery or just screwing in the cover on your light switch, you've used feel to apply a preload to a bolted joint. So I want you to think about what accuracy you think you have when applying a preload to a bolted joint. And then see if you're surprised when I tell you that on average that accuracy is about plus or minus 35%. And we're going to give this a relative cost of 1, and we'll compare the cost of everything else to this first method. Okay, so plus minus 35%, not great, but not terrible. And if you have a well-trained operator, you could get probably higher accuracies than even this. All of these numbers are from the Industrial Fastener Institute's reference, and I will link that in the description of this video so you can check that out and see how they got these numbers. All right, so next up, let's talk about a torque wrench. If you've ever worked on your car, you've probably used a torque wrench to tighten up the nuts on the wheel or possibly some other component of your vehicle. So torque wrench, I want you to try to guess what you think this accuracy is, and then I'm going to tell you that it's about plus minus 25%. And usually when I say this in class, students are pretty surprised because this is a very common method for measuring torque, and we think about it as being very accurate. But in reality, there is about a plus minus 25% accuracy to a torque wrench. All right, so next up we have turn of the nut. And if you're not familiar with this method, essentially what it is we tighten up our bolted joint until it's hand tight, and then there's a specification for how far we want to turn the nut past that. So I'll try to quickly draw what I'm talking about here. So let's say this is our bolt. We are tightening it up. In our procedure, it says that we need to use turn of the nut method, and we're going to rotate it 180 degrees past hand tight. So what you do is take a Sharpie or some kind of paint marker and mark a line going down the head of the bolt onto the member that you're clamping on, and then we would tighten this bolt 180 degrees until our lines look like this. Okay, so it's just a different way of measuring the preload by using a pre-described rotation of the bolt or the nut. They have these pockets of kind of plastic resin maybe embedded into the washer, and when you reach the preload that you'd like to achieve, they kind of seep that material out. So, and it's usually colored a bright color, so you see this like bright orange material coming out of the bolted joint when you achieve the proper preload. The accuracy on those is about plus minus 10%. The relative cost, though, is 7. So we've got to buy these special washers, and you can imagine they've got to be pretty precisely engineered and manufactured to achieve this function where they indicate at the proper preload. And so they're relatively expensive compared to the other methods we've talked about. Next up, we can look at fastener elongation. So fastener elongation is a method where we measure the length of the bolt before we tighten it up, and then we tighten our bolted joint, and then we measure again what the length of the fastener is after tightening. So let me try to draw this quickly, just so you know what I'm talking about. So here we first take a pair of calipers and measure the length of our bolt. Then we assemble our bolted joint. We tighten. As we tighten, this bolt is going to elongate, right? As we tighten the nut, we're stretching the bolt, we're clamping down on the members. And so after we finish tightening, then we remeasure the length of this bolt again. And the difference in the length will tell you essentially the strain on the bolt, and you can use that to back out the clamp load. So this method is fairly accurate. We've got plus minus about 3 to 5% accuracy, but the relative cost is 15. This is for a couple reasons. First of all, the labor involved in measuring the length of each fastener before and after assembly. And also, you've got to design your machine, or your bolted joint at least, to be accessible to a pair of calipers. So I've got to be able to get into this joint as I've drawn it and place, my calipers on the top and bottom here. And so if my top and bottom of the bolt are not easily accessible, then I've got to redesign the whole bolted joint to be able to use this method. So that's why the relative cost is fairly high. And then lastly, we have strain gauges, which I think most people will be familiar with. This is an instrumentation method where we simply apply strain gauges to the smooth section of the bolt. You're not going to want to apply it where you have your threaded portion of the bolt. And the accuracy of strain gauges is typically about plus minus 1%. Of course, that depends on the strain gauge that you end up purchasing, so you can go by the accuracy from that manufacturer. Maybe you get a little bit better, but the relative cost is high. It's about 20. We've got to do instrumentation for strain gauges. You've got to, assemble the bolted joint with the strain gauges installed. You've got to link that up to some kind of data acquisition software. Somebody's got to, analyze that data, convert it into a clamp load value. So it's a relatively expensive method to use, but of course we get very good accuracy out of it. So that's our trade-off. Now, given all these different methods, as we kind of already established, the torque wrench is a common tool used to indirectly measure preload. So we are going to want a easy to use equation to go along with our torque wrench value, which the torque wrench is going to report out a torque value, right? And so we need a relationship between that torque and the preload that is developed in the bolt so that we can use that preload value with all of the other equations that we've already developed for bolted joints. And we have a relatively simple equation we can use to do that. It is torque equals KFD. All right, so here's our torque equals to KFD. Of course, T is torque. K is a new variable, and this is referred to as either the K factor or the nut factor. Fi is our preload, and D is our nominal bolt diameter. So for the K factor, we can use table 8-15 in Shigley to find some published values for the K factor. If your bolt condition is unknown, you can usually use about 0.2. It's usually a reasonable estimate to start with. In table 8-15, you'll see different bolt conditions like zinc-plated bolts, lubricated bolts, cadmium-plated bolts, and K factors that go along with those conditions. If you're using a certain type of lubricant, often the lubricant manufacturer will provide an estimate of the K factor for that lubricant that you can use. But if your bolt condition is completely unknown, then you can usually estimate your K factor as being about 0.2. So that is all I had for this video. We talked about bolt preload, how to measure it, how to calculate what it should be based on the material, and how to determine what material you have based on the appearance of the bolt. So I hope that you found this video useful, and I look forward to seeing you in the next one.